Good luck. Oops. At school, everybody learned that light is an electromagnetic wave. It's like the ripples on the surface of a pond. When I drop a stone in, the ripples spread out. But when light is confined between two mirrors, then it's like when the ripples on the surface of the pond reflect off the bank. They can add together and get bigger. But they only get bigger if they line up properly. And they only line up if they're the same frequency. What that means is that only light that's of the correct frequency can fit between two mirrors. In my experiment, I take a single molecule of dibenzotyrrolene, a dye molecule, and place it between two mirrors. Now, when we shine light on a molecule, the molecule absorbs that light, and the electrons go from one state to another instantaneously. And what that means is the light that's absorbed isn't really a wave, because a wave is a big wiggle that happens over a long period of time, and the change in the electrons happens very quickly. The light that's absorbed is really a short packet, which we call a photon. Now, when the electrons go back to their original state, the process is reversed, and rather than absorbing a photon, the molecule emits one. Now, when a molecule's on its own, it absorbs and emits light of all different frequencies. But when we place it between two mirrors, it only emits light at the frequency that can fit between the two mirrors. The molecule changes its behavior due to the presence of the mirrors. It's absorbing and emitting light like a photon, but the light is bouncing off the mirrors like a wave. Now, if we take one of those mirrors and make them only partially reflective, then the molecule, the photons that are generated by that molecule, can leak out the cavity. And we can do tests on that and use them to do other things. This stream of single photons obeys quantum mechanics. So that means they can do weird things like be in two places at once, or one can affect another over very large distances. It also means that we can use them for new and interesting technologies. We could use them to build a quantum computer, a machine that does calculations with light instead of electricity, and can dwarf the capabilities of some of our normal classical computers. Or quantum-enhanced metrology, where we can measure things without even looking at them. Or absolutely secure communication, some implementations of which are being used right now. 100 years ago, there was a revolution in understanding, which means that we all now walk around with a computer in our pocket. And now we're going through a second quantum revolution, where we're learning to harness the world of the very small and bend it to our will. These molecules might just be one of the tools that helps us do just that. Thanks.